All right, so we're looking at Unit 7, and there's 3 different ways that we can do work. We're looking at the third one. In this one, work is the change in potential energy. And we can write this as work equals, or W equals, change in potential energy, that is delta PE. Change in potential energy. Potential energy means stored energy. It can take on many forms, such as elastic potential energy stored in a rubber band. It could be electrical potential energy stored in a battery. Or it could be chemical potential energy stored in the molecules of an acid. In this unit, when we talk of potential energy, we're speaking of only one kind. That is gravitational potential energy. Objects have gravitational potential energy if they are not sitting on the floor. An object sitting on a shelf has potential energy. An object on the top shelf has more potential energy than an object on the middle shelf. And we define potential energy using the definition of work. Remember, work equals force times distance. To lift an object weighing 50 newtons, which is sitting at rest on the floor, takes a force slightly greater than 50 newtons to get the object moving. Then a force of 50 newtons to keep it moving. Keep moving upward at a constant speed. Let's simplify this to say that to lift a 50 newton weight takes a force of 50 newtons. So our formula above becomes our force is weight, and our distance is height, vertical distance. And in symbols, W equals is the force of gravity, which is weight, times H, which is the height. Or work equals mass times the acceleration of gravity, which is the force of gravity together, times the height. And so potential energy is mass times the acceleration of gravity times height, which a lot of times we will abbreviate as M times G. Potential energy is mgh. Example A, find the gravitational potential energy of a 20 kilogram box sitting on a 3 meter high shelf. So we're looking for gravitational potential energy. That's mass times the acceleration of gravity times the height. We know the mass. We know the acceleration of gravity. And for now, let's just stick with 10 meters per second squared for a good approximation. And the shelf is 3 meters high. So the potential energy, 600, and our units, kilograms times meters squared per second squared, joules. 600 joules. B, how much work is done in lifting a 3 kilogram box from a shelf of 0.5 meters off the floor to a shelf of 1.7 meters off the floor? So let's look at the potential energy on the lower shelf. This is mass times gravity, acceleration 10 meters per second squared, times the height, half a meter. And it has a potential energy of 15 joules on this lower shelf. The potential energy on the upper shelf, mass is 3, acceleration of gravity is 10, new height is the only thing that changed, 1.70 meters, and it comes out to be 51 joules. And so the change in potential energy is the final potential energy minus the initial potential energy. And that is 36 joules. If we were going to draw a picture of this, I'd say here's the floor, here's the object on the 0.5 meter shelf, here's the object on the 1.7 meter shelf. The change in potential energy from here to here is 36 joules. So how much work did we do? 36 joules. In lifting this box, 36 joules of work was done. The box gained 36 joules of potential energy, and we lost 36 joules of chemical energy within our body. C. An object is moved from the first floor to the second floor of a building. Which method results in the most work done? Carrying up a flight of stairs, rolling it up a ramp on a set of wheels, or sending it on the elevator? Which one results in the most amount of work? So here is our options. So the first one is carry it up a flight of stairs, something like this, and here's the second floor. From here to here, that's the height, that's h, the vertical distance. So there's the stairs. Next we can roll it up a ramp. So here's a long ramp, could be on a set of wheels. Our third option was the elevator. So, maybe it's just a lift like this. They all get to the same place. They all have the same vertical height. The answer is they require the same amount. Since the amount of potential increase is the same for the object, no matter the path it's taken. An object sitting on a shelf has potential energy. An object which is moving has kinetic energy. So when an object falls from a shelf, it begins losing potential energy and gaining kinetic energy. Is there a conservation of energy? Is all of the potential energy lost being changed to kinetic energy? So consider a mass m sitting on a shelf of height h. So here's the ground, here's the shelf, here's mass m, and this is the height above the floor, h. So sitting on the shelf, the potential energy of this box is its mass times the acceleration of gravity times its height. Sitting on the floor, mass is the same, gravity is the same, but height is 0, so its potential energy is 0. The change or loss of potential energy here is mgh. When it falls from the shelf of height h, it accelerates towards the floor. Using some old formulas, we can calculate some things, like its velocity just before hitting the floor. So if you think back several chapters, we want to know velocity and we know distance. We don't know how long it's going to fall. We're going to use this formula. Final velocity squared equals initial velocity squared plus 2 times the acceleration times the distance. So we know everything here except for final velocity. Since the initial velocity is 0, we can actually ignore that one and just say velocity squared equals twice the acceleration times the distance. So if we put in the numbers we're using, if we put in the letters that we're using right now, we have velocity squared equals 2 times g times h. Square root of that says velocity equals square root of 2 times g times h. So its kinetic energy just before hitting is, so here's kinetic energy, 1/2 times mass times the velocity squared. Let's use this for our velocity. Kinetic energy equals 1/2 times the mass times the square root of 2gh. We have to square this thing. So that's going to get rid of our square root. It's going to get rid of our exponent. The 2's will cancel. We end up with kinetic energy equals mass times gravity times the height. So sitting on the shelf, its kinetic energy is 0. Just before impact, its kinetic energy is mgh. The change or gain in kinetic energy is mgh. So is there a conservation of energy? Yes. Actually, since we neglected air resistance, we only have a conservation of mechanical energy. The air resistance would actually change some of the potential energy to heat energy. So not all of the potential energy would become kinetic energy. But this leads us to the law of conservation of mechanical energy. The total mechanical energy of a closed system is constant. Or in other words, the sum of the kinetic energy and potential energy is constant for a closed system. Now we've got this term closed system. This means no air resistance or friction. In other words, we could say kinetic energy plus potential energy equals a constant.